So to understand the convergence speed of convex function, I want to first introduce few concepts of convex optimization and convex function. Okay. First, strong convexity. We say that a continuously differentiable function f is a alpha strongly convex function if fx minus fy satisfy this inequality, so this less than equal to gradient of fx transpose x minus y, so the inner product between gradient of fx and x minus y, the difference x and y, minus alpha over 2 x minus 1 normed square, the Euclidean distance between x and y vector square. Okay, so what does it mean? Fy is greater than or equal to fx plus gradient of fx transpose y minus x plus alpha over 2 x minus y Euclidean distance square. Essentially, this part is the tangent function of your fx starting from the point x. So when you have x point here, this part basically the tangent affine function meet the affine function and the convex function f meet at point x comma fx. Okay, so since the function f is convex, we know that the function f is above the tangent line. And the strong convexity tells us the gap between the function f and the tangent line. Okay, so if alpha value is big, alpha is large, then basically the function f becomes more far from the tangent line. On the other hand, if alpha is very small, very tiny, the function f looks like almost linear, almost affine function, like this. Okay, so basically, when a function is alpha strongly convex, then with this the quadratic function, we can approximate the original function f, and this approximation always lower bound the original function f. So we start from this tangent line, and then add this square term here, then you will have this kind of quadratic function shape. And this dotted line, the affine tangent line plus this square term, always below the original function f. Okay. So next one is smoothness. So we say the continuously differentiable function f is beta smooth if the gradient f is beta ellipsis, and or your function satisfy this. So which means fy less than or equal to fx plus gradient fx transpose y minus x plus beta over 2 x minus y Euclidean norm square. So again, this is the tangent line. This is additional square term, quadratic function, right? So smoothness is opposite to the strong convexity. When you have function f, you draw the tangent line here. So this is this term. And when you draw additional quadratic term here, So basically this smoothness upper bounding the original function f. Basically beta over 2 x minus y Euclidean square always greater than original function f. Okay. So basically usually people say alpha strongly convex and beta smooth property tell us the curvature of your function f. As alpha grows up, we get more this shape, more high curvature structure. As beta decrease, we get more flattened structure. Okay. And of course, alpha always less than or equal to beta because function f always upper bounded by beta over 2 x minus 1 x minus y Euclidean norm square. And this is lower bounded by alpha over 2 x minus y Euclidean norm square. So alpha always less than or equal to beta. And more formally, we can define alpha strongly convexity and beta smoothness using second order characteristic of convexity. Okay, suppose that domain of f is open and f is twice differentiable, so we can define the Hessian matrix. And the Hessian matrix, when the Hessian matrix is positive semi-indefinite always, then we can say f is convex. And with the convex function, if the Hessian matrix eigenvalue is always upper bounded by alpha, then we can say function f is alpha, always upper bounded by beta, then we can say function f is beta smooth. And the Hessian function is always lower bounded by alpha, the eigenvalues of Hessian matrix always lower bounded by alpha, then we say the function f is alpha strongly convex. Okay, so with this notation, you can say Hessian of fx always upper bounded by beta times identity matrix, always lower bounded by alpha times identity matrix. Here this notation means, so when we say A less than or equal to B matrix in terms of positive semi-definite sense, then we say B matrix minus A always positive semi-definite. We can say with this notation, we can say B minus A is positive semi-definite. So with this notation, we can say beta times identity matrix minus Hessian matrix always positive semi-definite. And to do this, we always have eigenvalues of Hessian matrix less than or equal to beta. Okay, so from the Hessian matrix, we can easily, if we can easily find the Hessian matrix, and if we can find the largest eigenvalue and smallest eigenvalue of the Hessian matrix very easily, then from that we can say, okay, function f is alpha strongly convex and beta smooth from this. Okay, so the quadratic function x minus a square with any constant a, this is very nice function. So as we discussed earlier, this is very simple optimization problem, and even with gradient descent algorithm, we can find a solution with any starting point with one single update. So why this is easy? We can explain this using alpha strongly convexity and beta smoothness term. So basically, we can easily check alpha x minus a square is 2 smooth and 2 strongly convex. So alpha is equal to 2 and beta also equal to 2. So when beta and alpha is very close, even equal, then the problem usually very simple, and gradient descent algorithm can converge to the optimal point with a very few steps. Okay, so in the remaining lecture, I will explain the convergence rate of the three cases. One is we have no assumption on alpha and beta. Second case, we have beta smooth property. And third one is the case we have alpha strongly convex and beta smooth. The three cases will have different convergence rate. And of course, the third one show the most strongest condition and convergence rate, and we will discuss.